Hello everyone. This is part 2 of topics 1 through 3 of exam 1, and we stated the differentiation formulas for the natural log of x and the natural log of u here, and we had proven the derivative of the natural log of x, and you'll be required to prove that theorem in the future, but I will certainly make you aware of it when the time comes through our Zoom lectures. And look at some examples now of using the two main formulas. So these two formulas you must remember, they're considered common knowledge again, and so the derivative with respect to x of the natural log of x is simply 1 over x, and then when we want the derivative with respect to x of the natural log of u, where u is assumed to be a differentiable function of x, the easiest way to remember it is just simply that the log goes away, we get a fraction, put u in the denominator, and its derivative, which I will denote as du dx, goes in the numerator. So for our first example, it's identically fitting that form for the natural log of u. And so dy dx, y prime, whatever you prefer. Again, log goes away, fraction, u in the denominator, and in this case, that is the 1 minus x to the 5th, and then its derivative, minus 5x to the 4th, goes in the numerator. And so that would be all there is to it. And you can see how the formula works. That is, there's a u in the denominator and du dx, the derivative of that u, in the numerator. Okay, the second example, I want to point out something special. You're going to hear me say quite often that you should never differentiate the product. You should never differentiate the logarithm of a product, quotient, or power, except when the argument is linear. Now, that doesn't mean you can't have product rules and quotient rules and power rules, as we're going to see. But if the argument is a product, quotient, or power, as we'll see in subsequent examples, you want to simplify before differentiating by using the algebraic log properties. Unless the only exception is if the argument is linear, such as this example where we have 7x. So I'm going to treat this initially as just natural log of u. And so I'm going to be lazy here, say y prime, using the natural log of u formula once again, u in the denominator, 7x, and its derivative, 7 in the numerator. And you can see that would simplify to 1 over x. Now, alternatively, I just want to show you this. If you did use log properties first, then y equaling natural log of 7x, you could treat the 7 as the m and the x as the n, and then this would be the natural log of 7 plus the natural log of x. But then the natural log of 7 is just a number, or in other words, it's a constant. Type it in on your calculator, you get some crazy decimal. And the derivative of a constant we know is 0. So therefore y prime would be 0 plus the derivative of the natural log of x, which is 1 over x, giving us 1 over x. So the same result. But you can see it's much easier just to think of it in terms of the natural log of u. So if the argument is linear, treat it that way. In terms of the natural log of u, no need to use the algebraic log properties, but we'll see cases in the future where log properties come in handy. Alright, so as we've said before many times, what you need to do is just be able to look at a function, decide what's the primary rule of differentiation, and once that's determined, just follow through with it, and anything you encounter along the way, you just simply deal with when you get there. So when we look at this example, maybe your focus is on the more elaborate function, natural log of 3t, which is a function of x, t cubed, also a function of x. Treat them as u and v, and we're going to need the product rule. So therefore, by the product rule, g prime of t will be the first factor, t cubed, derivative of the second. Okay, we're differentiating the natural log of 3t. So again, the formula, fraction, log goes away, argument, 3t in the denominator, its derivative 3 in the numerator. By the product rule, plus the second factor, natural log of 3t. Go through some parentheses around that, then times the derivative of the first and the derivative of t cubed, 3t squared. And so with regards to the product rule, there's uv prime plus v and u prime. And again, if you perform it in the opposite order, that's fine, but that's the way I like to do it. Okay, simplifying, can cancel the 3's, can also cancel one factor of t here, so we're left with t squared, and then plus we want to bring the 3t squared out in front of the natural log of 3t. And you could stop right there, but if you wanted to go further, greatest common factor is t squared, you could factor it out, and to get the first term we need a 1, and then plus to get the second term we need 3 natural log of 3t. So again, double bars mean you could stop, you get full credit. If you want to do the extra factorization, make it look prettier, that's fine. Okay, so next example, hopefully it's easy to identify this as a quotient, u over v. And so by the quotient rule, h prime of x would be fraction, start with the denominator, x to the 5th, derivative of the numerator, again log goes away, fraction, argument 5x in the denominator of that fraction, and its derivative 5 in the numerator. So that's denominator, derivative of numerator, now minus numerator, natural log of 5x, derivative of the denominator, 5x to the 4th, and that's all divided by that denominator, x to the 5th, as a quantity squared. Okay, with regards to the quotient rule, here's your v, this is our u prime minus u v prime all over v squared. Okay, making it look a little bit better, we can cancel the 5's, can cancel an x, we get x to the 4th, and then minus, bring the 5x to the 4th out in front of the natural log of 5x, and that's all over. Make sure you square this x to the 5th. If you leave it as that, it's going to take off credit. You should know power to a power, of course, we multiply the exponents, so x to the 10th. And you can go further with factorizations, but I'm not going to bother, that's sufficient. Okay, you'll notice when I give you examples, I generally like to give you one of each type. The next example, that is, if it's not a basic formula, it's one of the 3 major players, products, quotients, or powers. And hopefully here you can see we have a function of t raised to a power, so u to the n, general power rule, chain rule, whatever you prefer to call it. But as I've stated in the past, I like general power. Okay, when you perform the general power rule, be careful. Okay, first off, one thing, if I could say y prime, but I want to use differential notation. And this would be dy dt, because t is the independent variable that we're differentiating with respect to. And when you perform the general power rule, just make sure you're careful not to differentiate too early. That is, the rule says that you swing down the exponent, and then it's the same function, in this case 1 plus natural log of 2t, to the power 1 less, in this case would be 4, and then the derivative of the inside. And term by term, derivative of 1 is 0, derivative of the natural log of 2t, again the formula for the natural log of u, log goes away, we get a fraction, argument 2t in the denominator, its derivative 2 in the numerator. So with respect to the general power rule, there's nu to the n minus 1, And then in this case, formally, we should say du dt. So to simplify this, you could do a variety of things. Let's just say d by dt is, and I'm going to leave it as a single fraction. I'm going to cancel off these 2's. Only thing in the denominator would be a t, and then we'd have 5 times the quantity, 1 plus natural log of 2t to the 4th left in the numerator. Alright, now in this example, when you read this, make sure you read it as obviously y equals, but it's the sign, and then the next thing you should say is of. So it's the sign of this function of x. It really doesn't matter what this is. The important thing is you understand this is the trigonometric function sign that's an operator. So it's always the sign of some argument, as we've talked about in the past. So in terms of a basic formula, this is just sine of u. And so dy dx, I'm going to be lazy, say y prime, derivative of sine, cosine, same argument, natural log of 5x, then times the derivative of the argument. So now we're differentiating the natural log of 5x. Again, fraction, log goes away, 5x in the denominator, its derivative, 5 in the numerator. So with regards to the basic formula for sine of u, its derivative cosine u, and of course, by the chain rule, du dx. So here, y prime is, okay, again, you could write it in a couple different ways. I'm going to choose to write it as a fraction, cancel off the 5's, x in the denominator, and cosine of the natural log of 5x in the numerator. Okay, a special property here, one you really don't need to worry too much about, but needs to be stated, is a theorem for the derivative with respect to x of the natural log of the absolute value of u. Turns out you really don't need to worry about the absolute values. It's the same formula as the natural log of u. That is, you get a fraction, log goes away, u in the denominator, its derivative, once again denoted by du dx goes in the numerator. Let me clean up that du a little bit. Okay, so, and that could easily be proven. Just take the two cases where u is positive and where u is negative, and it works out. So don't worry about them. The reason why they're in there is because generally when you have trig functions as the arguments of the logs, because they could be positive or negative, and remember, we can only have the natural log of the positive quantity. So this gives us basically more of the domain. But it's the same formula. So this one's fitting basic formula for the natural log of the absolute value of u. There's actually a mistake here. It doesn't happen too often. But notationally, let me call this f of, I don't want to call it f of t because there's an x over here. Let me change that. F of x. And so f prime of x would be, okay, same formula, fraction, tangent 3x, the argument in the denominator. Okay, now the derivative in the numerator, so we call the derivative of tangent, secant squared, same argument 3x, don't forget, times the derivative of the argument, 3. So an acceptable answer, f prime of x, would be, let's say, 3 secant squared of 3x over tangent 3x. So that's acceptable. But sometimes the textbooks will use identities. So let me go off to the side here and say I'm going to simplify. So remember, double bars are good enough, but simplify with identities. So starting with the answer that is again acceptable, 3 secant squared of 3x over tangent 3x. I'm going to change everything to sines and cosines. So 3, and then secant is 1 over cosine, so that secant squared would be 1 over cosine squared of 3x. And tangent is sine over cosine, so sine of 3x over cosine 3x. So simplifying further, leave the 3 way out in front. Got times 1 over the secant, cosine squared of 3x, and then times the reciprocal, cosine 3x over sine 3x. We could then cancel one factor of cosine. Let me do it that way. And we'd get 3 times 1 over cosine 3x times 1 over sine 3x, and then we could transform the cosine, 1 over cosine and 1 over sine back. 1 over cosine is secant, and 1 over sine is cosecant. So 3 secant 3x, cosecant 3x. So the algebra or trigonometry using the identities more complicated than the actual calculus. So strive to get the answers in the back of the book, but realize, again, I'm majorly concerned about the calculus, so stopping right here at the double bars will be fine. Okay, going to the next page. Here's what I meant by never differentiate a log of a product, quotient, or power. That is, you want to use the algebraic log properties before differentiating. So in this example, well, first off, you're going to want to rewrite this as the natural log of t cubed and then t to the 4th minus 1 square root 1/2 power. And there was t cubed there. And it's understood that the argument is the product of t cubed and this quantity. Now, if you were just to use the formula for the natural log of u, this would turn out to be a little bit cumbersome. And so, therefore, we're going to take advantage of the algebraic log properties to simplify before we differentiate. The reason why it would be cumbersome as it is because when you take the derivative of this, you need the product rule, but then within the product rule, you need the general power rule. On this one, it just gets messy. So let's use the algebraic properties. Now this would still be f of t because we're not doing any calculus. So we would have natural log of t cubed and then plus the natural log of the quantity t to the 4th minus 1 to the 1/2 power. But we can go further with the algebraic log properties because remember we have the power property for logs. So therefore f of t can be written as 3 natural log of t plus 1/2 natural log of the quantity t to the 4th minus 1. And now that we have the arguments written in terms of the simplest things possible, now we'll start the differentiation process. So now it's f prime. So notice it goes in f prime in here. This was just algebra. 3 tags along, derivative of the natural log of t, 1 over t, plus 1/2 tags along, derivative of the natural log of this quantity, fraction, log goes away, quantity t to the 4th minus 1 in the denominator, and its derivative for t cubed in the numerator. And just making it look a little prettier, f prime of t would be, let's say 3 over t, plus the 2 can cancel with the 4. We'll be left with 2t cubed in the numerator over t to the 4th minus 1. So take advantage of those algebraic log properties. Here's another example. And here we'll use the general rule initially. See if there's anything worse than just some function of x in here as the argument, use the log properties. I'm going to take advantage of the general property we talked about earlier. There's 3 factors here And remember, when you break them down, if there's a factor in the numerator, when broken down, the coefficient of the log will be positive, and if there's a factor in the denominator, when broken down, the coefficient of the log will be negative. So this becomes natural log of x squared plus the natural log of the quantity x cubed minus 1 to the fourth, but then minus natural log of the quantity 2x minus 7 to the fifth. And we can go further. This would still be y. Use the power property. 2 natural log x plus 4 natural log of the quantity x squared minus 1, and then minus 5 natural log of the quantity 2x minus 7. Now we can differentiate. So now dy dx is equal to, right, the 2 is going to tag along as a constant multiple. Derivative of the natural log of x, 1 over x. Go to the next term, plus 4 tags along as a constant multiple. The derivative of the natural log of this quantity, fraction, log goes away, quantity x squared minus 1 in the denominator, its derivative 2x in the numerator. And then we have minus 5 tags along as a constant multiple, derivative of the natural log of this quantity, fraction, log goes away, 2x minus 7 in the denominator, its derivative 2 in the numerator. And then just to make it look a little prettier, say 2 over x plus 8x over x squared minus 1, and minus, we'll say 10 over 2x minus 7. Sorry, those last few steps, wasn't paying attention, and I may have written some things down without you seeing them, so I'll let you catch up there. Alright, so I think I'm going to stop it right there. We've got a little bit more left, probably only about 10 minutes, but it's important, and I don't want to make these videos run too much more than about 30 minutes each. So I'm going to stop right there. We'll come back and we'll do a part 3 for topics 1 through 3, and then finish up. That'll finish up our discussion for differentiation and logarithmic functions.